Alright, in this video we're going to talk about rotational energy and introduce a new quantity referred to as moment of inertia. Alright, so let's get started with kinetic energy. Okay, now in terms of energy, you'll recall that there are two main types. You have kinetic and potential. Potential is the stored energy, the ability to provide energy and transform it into other forms, and then kinetic energy is the energy of moving objects. So for this, in terms of rotation, it only really affects the kinetic energy of the object, because not only can an object move horizontally, but it can also rotate, and so we have to understand how to do a rotational energy. Alright, so to start off with, so imagine a solid object, okay, and so just a solid disk that is rotating in some direction. So we'll just say that it's kind of rotating. We'll do it in positive direction just to make all this a little bit easier. So it has an angular speed counterclockwise. Okay, and has a radius r to it. Okay, so it's a solid object. It has a mass to it. And for right now, we'll say that it's just kind of sitting in place. In other words, this pivot, this center point, is fixed. It's not moving horizontally. It's just spinning in this location. Okay, if we wanted to calculate what the kinetic energy of this thing is, we'd essentially have to look at each individual piece of mass and how each of those masses are moving in the circle. Okay, so if I look at this little mass here that I've marked, we know that at this point in the circle, it's got a tangent velocity. And then somewhere else we have, so say at the edge of this circle, it has a tangent velocity. And then somewhere closer to the center, it has a tangent velocity as well. Now remember that the tangent velocities are going to be different depending on where you are from the center of the circle. The further out you are, the greater your tangential speed. Okay, so there's all these different things going on. And so if I wanted to know what the kinetic energy is of this entire system, I would have to find the kinetic energy of each piece of mass. Okay, for as many masses that are in there. Now, it's easy to think that we might be doing a calculus concept here because there's really an infinite number of masses, but we're not going to go quite that detailed just yet. Okay, but for now, we're going to look at this expression and go, okay, so we've got all these different angular speeds, all these different kinetic energies. What we're going to do right now is we're going to look at all these different kinetic energies and figure out, again, the totals. So first thing I'm going to do is relate that each tangent velocity, remember, can be found by doing its radius times the angular speed. Now the reason I'm going to do that is, remember, anywhere on this object, doesn't matter where the radius is, the angular speed is the same. So this gives me 1/2 m1. Then when I plug this in for the velocity, I get r1 squared times the angular speed squared. Do the same thing for the second mass. That would be r2 squared and the angular speed squared. And then this would continue for as many masses as there are. Okay, so if I factor out the things that are constant, you'll see that I have a 1/2, and then I have this product, m1, well, rather than saying, well, no, we'll do that. So m1 r1 squared plus m2 r2 squared plus all the other products of m's and r squareds times the angular speed squared. Again, the angular speed was the same for every single object, or every single mass in this object, because when it's rotating, the entire thing is rotating at the same speed, regardless of where you are from the center. Okay, so from here, what we've come up with is a formula that says 1/2 and then all this mess in parentheses. Well, it's really a summation of the products of m r squareds times the angular speed squared. Okay, where this product in parentheses we refer to as the moment of inertia. Okay, and as a variable, we label that with a capital I. Okay, so we get rotational kinetic energy is simply 1/2 this moment of inertia times the angular speed squared. Okay, now it's really that easy, but we need to talk a little bit more about what this moment of inertia actually is. Okay, and to give you a sort of a hint, you'll recall that most of our formulas that we came up with in linear form, like kinematics, translates to rotational by just simply substituting rotational quantities, right? So just as an example, right, if I wanted to find the velocity of an object, we have the kinematic equation to do that. And if I want to do it in rotational form, I simply substitute all of the rotational variables, and it's pretty much the same formula. Well, if you'll notice, the same thing applies here. Okay, if we look at the normal kinetic energy that we came up with in the past, the linear version of that, it would be 1/2 the mass times the velocity squared. Now you'll notice the velocities switched out just like they would have in kinematics, and so there's got to be some connection here between mass and I. Okay, and so let's talk a little bit more about what this I actually means. Okay, so I stands for your moment of inertia. Okay, now if you remember, inertia was an object's ability to resist a change in motion, right? If an object's at rest and it's hard to make the object move from rest, then it has a lot of inertia, right? We talked about, this was back in forces, we use the example of a train. A very large train car at rest is very difficult to move from rest. Similarly, the large train car, if it's moving, would be very difficult to stop because it has a lot of inertia in its movement. Okay, and the quantity that we assign to inertia to give us an idea of how difficult it would be to change its motion was the mass. Okay, so when we look at this new idea, this moment of inertia, okay, basically it has a very similar meaning. So inertia is an object's ability to resist a change. When we're talking about moment of inertia, this is an object's ability to resist a change in rotation. Okay, so if we're looking at a wheel, for example, we've got a disc to represent a wheel. Okay, and it's going to rotate around this center axis point, depending on where the mass is located, right? For example, if this was a wheel with a very thin rim and nothing internal, right? Like it just has spokes kind of going out to hold the wheel in place, but we concentrate all the mass out here in the edge of the wheel. Okay, and maybe it's not even distributed evenly. Maybe half of the wheel is more massive and more dense than the other. Okay, then it follows that as we try to grab, say, this end of it and try to rotate, we will feel a lot of resistance versus if we grabbed the heavier end and tried to rotate that end. Okay, and that's what we mean by the moment of inertia. It's the object's ability to resist a change in its rotation. Okay, and that's equivalent to what we defined as mass. Mass was a quantitative way to talk about how difficult it is to change the motion of an object. So moment of inertia would be how difficult it is to change the rotation of an object. Okay, and so that's what we mean when we say kinetic energy of a rotating object. Again, if the linear kinetic energy was 1/2 mv squared, then the rotational version should be the rotational analogs, which would be an angular speed and this rotational inertia. Okay, now in terms of knowing what I actually is, there's a couple ways to do it. We can calculate it, or we can let the book do calculations for us. Inside the book, you'll find this table. Okay, and in this table, it gives you moment of inertias for random objects. And again, notice uniform density. Okay, and we talked about that with center of mass. Okay, and so I don't know if you can clearly see all of these, but it's in your book. It's actually on page 300. Okay, and it's a book you can reference whenever you need to, especially for the homework problems. Now, on AP questions, you're going to be asked to do one of two things. You're going to be asked to either calculate this, or you will be given what the moment of inertia is directly. Okay, so memorizing these is not that important. But when you're doing the homework, this is where it's going to be telling you to reference. Because it'll say things like a wheel, which is hollowed out, so that would be like a cylindrical hoop. It might talk about a solid disc that's rotating, so we're talking in this one, it could be a stick rotating about its center. Okay, it could also be a stick rotating about its end. Okay, it could be a door on a hinge. I mean, it'll give you different objects in the problems. You'll have to know where to go on this page to figure out the moment of inertias. All right, so one of the ways that you're going to apply this is in terms of when you're looking at energy. Okay, remember, total mechanical energy was the sum of your kinetics and your potentials. Now, it's possible that you have an object fixed that's just rotating, which means your kinetic energy would be in rotational form, and the potential energy would still be based on whatever type of potential energy we're talking about, elastic, gravitational, electrical, whatever the case is. Okay, but for our purposes, for the most part, we're going to stick with gravitational. So you'd have mass gravity times the height. Now, what's important to understand here is we're talking about the location of its center of mass. Okay, so if you were to have something like, for example, say a stick that's fixed horizontally, but the pivot is over here on the left end, right, and it can rotate through, and we want to know, well, how fast is it moving when it reaches the bottom? Okay, the center of mass is changing its height as it swings through. Okay, but in terms of the rotational inertia, it's not rotating about the center, it's rotating about the end. Okay, and so that's essentially one of the differences in how we're going to calculate energy problems when it comes to rotational. Okay, where the rotational energy was 1/2 moment of inertia, angular speed squared. Okay, so now let's talk about how we would calculate the moment of inertias, because it's all fine if we're using these common shapes, but you're not going to be asked all the time to do common shapes. Okay, so let's practice a little bit of that. How do we calculate a moment of inertia? Well, we described on the other page, you'll remember, when we first showed what I actually equals, the moment of inertia was the sum of the products of m times r squared. Okay, so now what that means is imagine you have, let's say a dumbbell set. Okay, you've got a bar and it's got 2 weights on the ends of it. Okay, now we're going to assume that the bar itself is massless just to make it easier. Okay, and let's say that there are 2 10-kilogram masses on each end. Now notice what happens when you change the rotation axis. Let's say that we start off with the rotation axis right through the middle. Okay, that means this thing can rotate, okay, in either direction, clockwise or counterclockwise, around this center point. Okay, and we'll say that the full length of this thing is, I'm going to exaggerate this. We'll just say it's a meter. Okay, so maybe it's more of a barbell than a dumbbell, but that's okay. We'll say it's 1 meter in length. So if I want to calculate the moment of inertia, okay, so m is obviously the mass, but r is the distance measured from the mass to the pivot, okay, or the rotation axis. Okay, so let's label these masses. We'll say that the one on the left is mass 1, and the one on the right is just mass 2. Okay, so if I want to calculate the moment of inertia here, it would be the sum of these two things. It would be m1 at r1 squared plus m2 at r2 squared. Okay, so mass 1 is 10 kilograms, and it is located half a meter away from the pivot point. Because if the pivot's right in the middle, then that means the mass is exactly half of that distance away. Okay. The other mass is 10 kilograms, and it's also located at half a meter away. All right, so when we crunch this out, we get 2.5 kilogram square meters and another 2.5 kilogram square meters for a grand total of 5 kilogram square meters. Now, it might not make much sense as to how much resistance and rotation that number actually is, but it's easier to understand its impact when you compare it to a different moment of inertia. In other words, take the same setup, so two masses, we'll say, again, 10 kilograms each, separated by 1 meter from a massless bar. But this time, we're going to rotate this thing through one of the ends. So instead of rotating about the middle, what if we rotated it about, say, the right end? What does this do to our moment of inertia? So same formula, and we'll keep the same 1 and 2 labels. So m1 r1 squared plus m2 and r2 squared. Mass 1 is still 10 kilograms, but now it's located 1 meter away. Mass 2 is 10 kilograms, but it's located on the pivot point, so its distance r is 0. So when I calculate this, I get a grand total of 10 kilogram square meters. Now compare these two. Okay, what this is telling us is it is more difficult to rotate an object about its end than it is to rotate about its center. Okay, and that's essentially how we're calculating moment of inertia. And you could feel this with a textbook. If you were to grab your textbook in the middle, okay, so imagine that this rectangle is your textbook. If you were to pinch it with your fingers on both sides of the book right in the middle and try to rotate it, you would feel a little bit of resistance because of how the mass is distributed from where you're pinching it. Then, if you were to take that same book and pinch it on the end and try to rotate it, make sure you do this with outstretched arms and away from your face, and you try to rotate it, you're going to find that it's much more difficult to rotate this thing. Okay, and that's essentially how we calculate moment of inertias. The more applied, or the more general way of doing this calculation is when you have an object of continuous mass distribution. Okay, a solid object instead of just point masses located on a line. Okay, and that's where we have to do a little more calc-based physics. Okay, so if we had the moment of inertia is mass times r squared, it follows that if we look at the tiny bits of mass located at some distance, this becomes an integral of r squared times of r squared dm. Okay, now if you remember in that table I showed you with all those different moment of inertias, this is where they come up with that. Okay, so for example, you might be asked and I've seen this on a free response question, they want you to confirm that if you've got a rod of uniform density of length L and mass M, and it's rotating about its end, they want you to confirm, showing all the steps, that the moment of inertia is 1/3 ml squared. Okay, so how do you go about doing that? Well, if it's the integral of r squared dm, okay, and it's uniform density, okay, and it's along a line, again, uniform density means that this ratio is the same everywhere along the line. Okay, so that means that dm is equal to m over L dx. Okay, and I know the formula says r, but for the sake of the variables, we're going to change that to x because it's along an x-axis. And dm was m over L dx. And our limits are going to be, well, the entire length of the rod. We're going from 0 all the way out to L. Okay, and so from this, we're going to work through it and solve for the moment of inertia. Okay, so m over L is a constant, so we'll pull that out. The antiderivative of x squared is 1/3 x cubed. And we have to evaluate it from 0 to L. So this becomes m over L times, it's 1/3 upper limit minus 1/3 lower limit. So we end up with 1/3 m over L times L cubed. Well, one of these L's is going to go away, the one on the bottom, and just one of them on top. So the end result is 1/3 ml squared. Okay, as it should be. Okay, so it's a process that you need to know how to do, but it's not so important that you, if you're weak on this area of doing the calculus, it's fine. There's not that many questions that are going to ask you to do the calculus, but every once in a while they like to pop up. Okay, now the next thing is, what do you do if an object is rotating around a pivot that isn't defined in that table? Okay, because in the table, for example, we had this stick rotating, right? And there was two options. You could either rotate it about the center, or you can have it rotate about the end. Okay, but what if you have it rotating somewhere in the middle of those two, or somewhere in between those two? Okay, how do you find the moment then? And so this is called the parallel axis theorem. Okay, so to get your orientation straight, by saying parallel axis, if you think about it, so there's a line that's kind of going in and out of the page at each one of these dots, and all those lines are parallel to each other. So if I have an axis, where the blue line is, or where the blue dot is, there's an axis going into the paper that is parallel to the center of mass line, where the red dot is. And that's essentially what the parallel axis theorem says. Okay, and it's actually a very easy process. It's simply saying that the moment of inertia here is equal to the moment of inertia at the center of mass plus the mass times d squared. And now d is how far away is the new axis from the center of mass. It's that easy. Okay, so if this was a rod of mass and length, and we'll say that this d is a small, say 1/4 L, very tiny amount, right? Well, through the center, if you look back at the table, it was 1/12 ml squared, so that was from the table. And then here we've got the mass of the stick times 1/4 L squared. So that's 1/12 ml squared plus 1/16 ml squared. Okay, so let's see, that would be 7/48 ml squared.